Okay, so acids and bases are things that you've dealt with all your life, but you may not have known that these things were necessarily acids or bases. For example, each of these four acids are found in fairly common household items. Ascorbic acid is also known as vitamin C. Citric acid is the acid that you find in things like oranges and lemons and limes. Acetic acid is also known as vinegar. And then sulfuric acid, which we've used in the lab before, and you've certainly heard of it, I'm sure, is also the acid that you would find in batteries in automobiles. Sulfuric acid also happens to be a major component used in fertilizers, detergents, plastics, etc. Bases you may not be as familiar with, but certainly you know there are some that are common household items. For example, certainly you know ammonia. Ammonia is found in a lot of household cleaners, more specifically in glass cleaners. It's what prevents the streaks actually from forming on glass when you clean it. And then sodium hydrogen carbonate, also known as sodium bicarbonate, is what is baking soda. Now, acids, though they vary tremendously in their chemical components, they all have some fairly distinguishable properties that would allow you to know that they are indeed acids. For example, they're sour, though I strongly urge you not to taste things in lab to determine this. Acids also burn you if they are strong acids and they get on your sort of an open cut or something like that. You may also recall that they react with metals and they usually form hydrogen gas. So if we go back to this very familiar reaction, this is something that we did at the tail end of the fall term and into winter term, where we put zinc into hydrochloric acid, and you can imagine, or you might recall, that we did the hydrogen pop test to confirm that hydrogen had been produced. And then lastly, they also conduct electricity, and that's because they ionize in water. A couple other things. If you were to do a litmus test using litmus paper, acids will turn blue litmus paper to red. And there are other indicators like phenolphthalein, which actually we'll get to in just a little bit when we start talking about the bases. So let's look at some properties of bases. So if you were to taste a base, they would actually have a bitter taste to them. But again, it's not something that I would recommend. However, I know that many of you probably have had your mouths washed out with soap because you have such nasty language. So you certainly have, I'm sure, tasted soap a little bit, and you know that it has a very distinctive bitter taste to it, and that's because of the base in soap. Oops, I didn't plan this right. I don't have enough room here. In terms of how they feel, it's actually, strangely enough, they're going to have a slippery feel. And this is sort of a strange sensation. What actually is happening there is that when you actually have a strong base on your fingertips, it's dissolving a little bit of your fingerprint and making it feel slippery in between. Unlike acids, they do not lead to the formation of gas when you combine with a metal. However, similar to what we see up there, they also conduct electricity. And once again, it's because bases will ionize. They'll break up into their ionic components. And then lastly, unlike the acids that turn litmus paper that is blue to red, bases turn red litmus paper to blue. I wish I could fit that in, but I didn't leave enough room here. But you should write that down. Litmus, red to blue. Also, the piece that I wanted to mention just moments ago, which is that in the presence of the indicator called phenolphthalein, shoot, I really should write that down here. And in phenolphthalein, if there's an acid present, it'll maintain its colorless characteristic, whereas if you have a base in phenolphthalein, which comes in an aqueous solution, then it'll turn pink. So pink with the presence of a base. All right. Now let's talk a little bit how we define these things at the submicroscopic level. These things called acids and bases. So it sounds sort of strange for me to talk about this at the submicroscopic level. Well, the reason why I say that is because what I just described moments ago in terms of the physical and chemical properties, that's sort of at a macroscopic level. This isn't even just at the microscopic because you wouldn't be able to see these through a microscope. So it's even smaller than what you'd be able to see visually in through a microscope. So there are two different ways in which we define acids and bases. The first one is called the Arrhenius definition, and the second one is the Bronsted-Lowry definition. So let's talk about the Arrhenius definition first. And for the Arrhenius definition, I want you to focus on product formation here. Product formation. And if that's the case, let's take a look at what happens when I dissolve something like HCl gas into water and see what kind of products form. Now this is a strange looking thing you'll see here in just a moment. I start off with HCl in the form of gas, can bubble it into water, and it's going to create this funny looking polyatomic ion plus the Cl minus ions, and it'll release a bunch of heat in this process. Now it's this that's important because this is called the hydronium ion, a new polyatomic ion that you need to get into your memory banks. And what I want you to notice with this hydronium ion, that simply what has happened here is the hydrogen associated with the HCl has broken off and it's connected to the water, so it becomes H3O plus, and then it's left the Cl minus by itself since it's lost its hydrogen. Okay, so that hydronium piece is very important. Now let's take a look at this in a slightly different way, just to make this absolutely clear what's going on. As you know, when HCl dissolves in water, it's going to break up into these two parts, hydrogen ion and a chloride ion as well. These are the dissolved parts, the ions of HCl. So it would look like this. You can see here that I have the HCl together, but that when it breaks up into the hydrogen ion, which I'm showing as a blue dot, and the chloride anion, which I'm showing as Cl minus. Now let's use these same sort of pictures to see what's going on if we were to look at this reaction going on up here. Okay, so here we have the HCl gas combining with our H2O, and where does this bring us? So the hydrogen ion pops off and attaches itself to the neutral water molecule, but because the water molecule was neutral and you have a positively charged thing going to it, this is no longer going to be just a neutral ion. It becomes a positively charged species, and then you're left with the poor chloride ion. Oops, I don't want it black. Undo. The poor little chloride ion all by itself as a negatively charged species there. Okay, so this is a funny looking thing here, this hydronium that we've just created. But I want you to know that that's exactly what's made every time you combine an acid with water. Shoot, I think I've been pausing and unpausing in the wrong way. Hold on, let me look at this. Indeed I was. I think you missed. Oh well. Anyway, you can see the definition there, and I think you had time to write it down as I was slowly writing it down. So now let's apply this to bases, and it's going to be our Arrhenius definition of bases, and that means we're still going to focus in on products. What happens in the formation of products here. So let's look at a fairly common, probably my favorite of all bases, sodium hydroxide. Okay, so in this situation you can see that I've taken my solid sodium hydroxide And I've shown you just the dissociation reaction that goes on here. So you assume that this is happening in water. And when it breaks up in water, notice that I don't have water here as one of the reactants as I did with the HCl above. That's kind of an important thing to understand. It's sort of happening in the background in this situation. In a moment, I'm going to show it with water as a reactant, but since you need to know both, I had to show you first this one without the water. And what's important here is that we have formed this negatively charged species, the hydroxide ion. And that, in fact, is the definition of an Arrhenius base, which is that it forms hydroxide ions in an aqueous solution. Let's take a look now at a different base before I write down that quick definition. So this situation, this reaction, it parallels what we just saw above with the hydrochloric acid gas combining with water in a much more obvious way. And so when you take a look at what's going on here, again, we know that the ammonia is going to be our base. And the reason why we know that it's an Arrhenius base is that the hydroxide ion is formed. Now, where does that hydroxide ion come from? Well, if you take a look at water, don't forget that water had H2O. It looks like this up here, right? So if you were to imagine I snap off this one hydrogen from this water molecule, that's going to leave me with just an OH, which is what we see right here. And where does that positively charged hydrogen go? Well, it sticks itself right onto the ammonia to become an ammonium ion. So you take one of these hydrogens and you give it to the ammonia, which forms NH4+, and as a result of losing one of the hydrogen, it becomes OH minus, or the hydroxide ion. So parallel definition is that bases will form hydroxide ions in an aqueous solution. So pretty simple, right? As long as you remember hydronium is for acids and hydroxide is for bases, then you got the Arrhenius definition down. Let's shift our thinking, though, to something called the Bronsted-Lowry definition, which focuses on what's going on at the reactants rather than what's happening with products. So the reason why we have to have this different definition is that I want you to note that the Arrhenius definition required that an acid and base be in an aqueous solution, but that's not always going to be the case. Sometimes you can have an acid or a base that's independent, or I want you to be able to think of it being independent of being dissolved in water, and still we need to figure out why it would be called an acid or a base. So let's take a look at this, and again what I want you to do is focus in on what the action is that's going on at the reactants levels, and in particular you're going to focus in on the movement of protons. So we have this thing here, and I'm deliberately not going to name it. Okay, I'm not going to tell you what this is, and we have water. And what we have with the Bronsted-Lowry situation here is we're going to have this hydrogen here associated with this reactant that will transfer itself to the water. Okay, so we have something going on at the reactants. The thing that's going on is the movement of a hydrogen ion to the water. And I think you can see this is a fairly predictable set of products that will be created. So you can see here that what I've done is I've created the ion of the CH3COOH, and I've created hydronium. So in terms of the definition regarding the Arrhenius definition, it still works here because hydronium is being formed here. But with Bronsted-Lowry, we're going to focus much more on who receives that proton versus who loses the proton recipient and the proton donor with regard to defining things. So with this being the case, the Bronsted-Lowry acid is going to be the species that donates the proton to the other substance. So in that way, this right here, the acetic acid, is going to be our acid because it's the proton donator. Just to be sure, I did a naughty abbreviation, BL, meaning Bronsted-Lowry down here. A little bit strange, huh? Seeing what I wrote there? That means water, in this case, becomes a base. So with Bronsted-Lowry, you're always going to have one thing that you can look at as the acid, and the other thing that receives that proton as being the Bronsted-Lowry base. Now let me show you what it means when we're dealing with things where water may not be involved at all. And in the case of the Arrhenius definition, if there's no water involved, we wouldn't be able to define something as an acid or a base, which is absurd because you'd still have acids or bases. So let's move this up out of here and let's take a look at this reaction. And you can see that this reaction involves two things that you already know in terms of acids and bases. HCl, you know, will form an acid when it's dissolved in water, but that doesn't mean that it's not an acid when it's not dissolved in water. And we have ammonia, which is also something that when combined with water will form a base, but by itself, why can't we call it a base? Well, we can with Bronsted-Lowry because in this situation, the donator and the acceptor are right here. You can see here that the HCl is going to donate its proton right to the ammonia, and the ammonia is going to be the acceptor. So as a result, going back to our definition of acceptors versus donators, where are we? Here we go. If the proton is the donator, if you're the proton donator, then you're the Bronsted-Lowry acid. And in fact, indeed, that's what this is, the Bronsted-Lowry acid. And if you're the acceptor, in the case of the NH3 will be the acceptor, then that makes you the base. So let's take a look. We don't really need to go further, but obviously since this is chemistry, we want to see the reactions occur. And you could imagine that this is then going to become the chloride ion by itself, right, because the HCl has lost its hydrogen, plus our ammonium ion. Both of these now, oh, actually, I don't even have to say that they're in an aqueous state because this need not take place in water. So I'm going to undo that little aqueous thing right there. All right. Now, it's unlikely that you'd have this happen just the two gases come together in the lab because that would be an incredibly powerful reaction. It would be very explosive. So typically you would have this combination in water anyway, in which case the Arrhenius and Bronsted-Lowry definitions work in both situations. However, let's take a look at something that is slightly different, but it's following the same rules as we just saw moments ago. So we just used these same examples moments ago when we were talking about the Arrhenius definition. But what I want you to now do is to focus in on being the donator versus the acceptor. So we know that HCl is going to donate its hydrogen to water, and that means you're going to form the hydronium ion and the chloride ion as well. And then we could look at this bottom situation and see a very similar situation where we're going to have the hydrogen donating the water donating its hydrogen to the ammonia. And that leads to the ammonium ion and the hydroxide ion as well. Now, these fit both definitions pretty nicely because you can see here that our Arrhenius definition says that you have to form the hydronium ion and also that you have to form the hydroxide ion, so that works pretty well. Now keep in mind, if we were just relying on that definition, notice that in this situation here, we haven't formed hydroxide or hydronium, which would then say, all right, well, I guess these things aren't acids or bases. And then we know that's absurd. That's not the case. That's why the Bronsted-Lowry becomes a little bit better definition to help us understand the difference here. But the reason I point this out is to make us focus in on what's going on with water. Because in this top situation, water becomes our base. Everyone see that? That water becomes the thing that accepts the hydrogen and therefore is a base. But in the second situation, water is the donator of the hydrogen ion, and so in this case, it's the acid. It's the acid to the ammonia being the base. In this case, the hydrochloric acid is the acid to the base of water. So water can be an acid and it can serve as a base in our Bronsted-Lowry definition. All right, that's it. I've given you way too much information, so I'm going to stop right there.